All right, guys. So hello and welcome to McLean 360. So over here, we have the topics that we are going to cover today. So please kindly join me as we go through together. All right. So we are going to begin with equilibrium of rigid bodies. Okay. So we are going to start with the equilibrium of rigid bodies. All right. Okay. So let's look at this problem which we have right here. Okay. So in this problem, all right. Okay, guys. So how can I solve this problem? All right. So the masses of the man and the driving bolts are 50 kilograms and then 36 kilograms. Is that right? Okay. So now we know that the mass of this man is 54, right? So the mass of this man is 54. Therefore, the weight is going to what? mass times acceleration due to gravity. Is that right? So that's going to be 54 multiplied by 9.81. And what is that? So 54 multiplied by 9.81. So let me make the calculator bigger. Okay. So let's multiply this together. We have 54 multiplied by 9.81. So what are we going to get? Okay, so if we have 54 multiplied by 9.81, what do we have? Okay. So we are going to get what? 529.74. Is that right? So 529.74 newtons. And that is the weight of the man. Is that right? And the driving board, so the weight of the driving board is going to be what? 36. So the weight of the driving board is going to be 36 multiplied by 9.81. What is that? So 36 multiplied by 9.81, that's going to give me what? 353.16. Newtons. Alright. Okay, so basically, this is the weight of the driving, the driving boat, or the driving board, and this is the weight of the man. Is that right? Okay. So now this is what we have to do. The question said we should sketch the free body diagram. So what is free body diagram? Now when we say free body diagram, a free body diagram simply means we are to draw the diagram and then we will free the body. Interestingly, what this means is that we are going to look at all the forces acting on the body. And then we will look at the, we are looking at the reactions at the support A and B. Is that right? Okay. So now this is what we are going to do. The free body diagram, I will not clean anything here. But I just want to show you that there are two things here. We have a ruler and then we have a hinge or a pin. Alright. So either you are going to call it a hinge joint or a pin joint. Alright. Now whenever I have a ruler, I will have only one reaction. So ruler has got only one reaction. And then a pin has got two reactions. Okay, maybe let's draw it again. So now let's draw it again. Okay, let's say I have the rod as this. Okay. So let's say that this is the rod. Now what happens is that at point A, I have a pin or a hinge. Is that right? Now, whenever I have a hinge, I'm going to get two reactions. Okay. So at A, I'm going to get a reaction along the X. Let's call it AX. And then I'm going to get a reaction along the Y. Let's call that AY. Is that right? Now, watch this. At point B, which is located at a distance 1.2 meters from A, there is a ruler. It means that if I walk all the way right here till I get to point B, somewhere here, I have got a ruler. Okay? And for a ruler, I have only one support for a ruler. So let's call this support reaction BY. Alright. And then the weight of the driving board itself, which is acting at a distance 2.4 from A. So that distance has been specified. So, okay, so from here all the way to here is 1.2, okay? But the distance from A all the way to where the weight is, that distance where the weight of the driving board is acting is given here. Now, interestingly, the weight is going to be 353.16. Is that right? Newtons. And then the weight of the man. Since the man is standing at the edge of the board, we can say that, okay, so the weight of the man can be assumed as a concentrated force, which is just acting here, of magnitude 529.74. Now, if you have been able to do this up to this point, then you have gotten, or you have got what we call the free body diagram. Okay. So now this distance all the way here is 2.4 meters. And we call this the free body diagram. So the free body diagram. So essentially what you have here is a diagram which has got all the forces acting on it. Okay. Now I want you to take care of this, please. Some students are always confused when it gets to this point. Whenever you are, whenever you are drawing the free body diagram, it doesn't necessarily mean that the direction of the force is known. So whenever you have an unknown force, let's say a reaction force, you can let it go in any direction. But after solving for the reaction forces, if you get negative, then it means the direction you chose is actually the opposite. Alright? So you just change the direction, that's all. Okay. So now our free body diagram is ready. Now what did the question say? The next part of the question says that we should determine the reactions at support A and B. Alright? So now we have to find the reactions at the support A and then B. Alright? So let's do that. Okay. So how can I find the reactions at the support? So the first thing you have to do is actually apply the laws of equilibrium. So laws of rigid body equilibrium. So laws of rigid body equilibrium. Now for a rigid body to be in equilibrium, summation of forces in all directions should be 0. And then summation of moments about any point in the plane should be 0. Alright? Now since I am dealing with equilibrium in 2 dimensions, then I'll say that summation of forces along the x in this direction positive should be 0. Then I'll call this equation 1. Is that right? And then I will go forward to say that summation of forces along the y, every force going up positive should be 0. Alright? Okay, let me bring it down. So I will say that summation of forces along the y, every force going up positive should be 0. And then summation of moments about a point, let's say point A, should be 0. Alright? Okay. So then let's start. So I'll get equation 1 from summation of forces along the x. I'll get equation 2 from summation of forces along the y. And then I'll get equation 3 from moment. Alright. So let's start. So summation of forces along the x, every force in this direction positive should be 0. Right? So let's go back to the diagram. Then you ask yourself, is there any force act on the body in the x direction? Okay, so this is your x and this is your y. So you want to ask yourself, is there any force which is actually in the x direction? Alright, is there any force which is in the x direction? Alright, so ax, right? But what is the direction? So you can see that ax is actually in this direction. Alright, it is going in this direction, so it's going to be negated. Alright, so minus ax. Is there any other force in the x direction? No. Therefore, we can clearly see that ax is actually 0. Technically, what this is telling us is that there is no reaction along the x. As a matter of fact, it means that there is no force in the x direction, because all the forces are being applied at along the y direction. Therefore, there is no force which is what in the x direction. Alright. Now again, let's sum forces along the y. So summation of forces along the y, every force going up should be positive is 0. Is that clear? Alright. So now this is what we are going to do. We will go back to the diagram. Then we will sum forces. Okay? We are going to sum forces. So if we see a force which is going up, then it is positive. And then if we see a force which is going down, then it is what? Negative. Is that right? So let's start with the forces along the y. Look at this. You can see that AY is coming down, so it is going to be negative. So AY is going to be negative because it is coming down. BY is going up, so it is going to be positive. And then I have this force of 353.16 newtons, and so it's going to come down, right? And then I have this force which is going down, so it's also going to be negative. Is that clear? So let's start. So minus AY plus BY, is that right? Minus, so minus 353.16, and then minus 529.74 should be equal to 0. Right? Now, is there any other force which we have not considered in the Y? No. Alright. So it means we are done. Is that right? Now, from here, I can say that minus AY plus BY should be equal to 353.16 plus 529.74. Alright? Okay. So when we get to this point, we will actually we have to add. Alright? So now let's add. Okay, now let's add. So let's pick our calculators. Alright, so let's pick our calculators, and we are going to add 353 so we are going to add 353 okay, so 353 okay, so we are going to add 353.16 plus 529.74. And what are we going to get? So you are going to get 882.9. So in other words, minus AY plus BY is equal to that. Let's call this equation 2. But I have two unknowns from one equation. Means that I cannot solve it, right? So then I need an extra equation which will come from where? Moment. Alright, so now we are going to some moment. Now most students do not know the difference between clockwise and anti-clockwise. Alright. Alright, so let's start with the moment. So we are going to some moment about A, but we are going to say that counterclockwise is positive, and this should be equal to 0 for equilibrium. Alright. So let's start. So we are going to start from okay, so now this is point A. Point A is here. This is point B, and this is the center of gravity, and then this is where the man is standing. So we want to some moment about point A. Why are we some moment about point A? So that we can be able to eliminate the reactions. Alright. If we don't some moment about A, we will not be able. Alright, we will not be able to do that. So let's sum the moment. Now, starting from By, the moment of By from A is 1.2, which is the distance, then I'll multiply by By. But what is the direction of the moment? Now, let's imagine A here. Okay, so imagine that you have point A here, and then there is point B. Let's imagine that this is like a rod, and then let's say you apply a force here, which is By. What is going to happen if you fix this point? You realize that if this is a rod, then this rod, if I apply a force in this direction, it is going to go in that sense, right? So basically that is going to be counterclockwise. So 1.2 By, which is actually positive. So 1.2 By. Now, with respect to the so we are done with By. Let's come to the next force, the 353.16 force. You see that with this force, what happens is that if this is C, now the distance from C to A is what? 2.4. So I'll multiply the 2.4 with the 353.16. But what is the direction? You can clearly see that if I fix so if I fix a point here, and then I have a rod right here, and then I apply this force downwards, then it is going to rotate it in that sense, right? Which is what? Clockwise. So basically this 353.16 force is going to cause a clockwise movement about A. Is that clear? Alright. So then if I multiply, so then if I multiply 353.16 by 2.4, what am I going to get? Alright. So 353.16 multiplied by 2.4. And that is actually so that is minus, right? So minus 847.584. So please, I want you to take your calculators and also check. Alright? Okay. Alright. So now basically alright, so basically we have the moment. Now let's look at something here. The last force to deal with is 529.74. Okay. So this 529.74 is creating a moment which will send the bar in this direction. Is that right? Imagine that you have this again. Let's say you have a rod here. If you apply the force, it's going to push it down, which will rotate it in that sense. So essentially, this is also going to be that is clockwise. But this time around, we are going to multiply the distance. Let's go back. If you look at this diagram carefully, alright. So if you look at this diagram carefully, you will see that. So the distance between the position of the man on the driving board and the distance from the hinge, that is what, 4.6. Is that right? So now basically you are going to multiply the distance with the force. So 529.74 multiplied by 4.6, and that moment is going to be what? A clockwise moment. Is that right? So if that is clockwise, okay. Alright, so let's do that one. So 529.74 multiplied by 4.6. So if you do it correct, you should get 2436.804. Alright. Okay. So now it means that we have been able to do the moment for all the forces. Therefore, we will equate this to 0. And then we will solve for By. So By will be 847.584 plus 2436.804. Then I will divide everything which is here by 1.2. And that gives me the value of By. So if you do everything correct, then your By is going to be 2736.99. So approximately your By is going to be 2737.0 newtons. Alright? So now we have been able to solve for By. So if you want your AY, what do you have to do? You go back to the equation and then you just solve for AY. So this one was supposed to be equation 3. If you substitute By into equation 2, then we can say that AY is what? 882.9. Okay. So let me write it well. So we know that minus AY plus By is what? 882.9. But if we solve, for AY, then AY is going to be By minus 882.9, which is what? 2737.0 minus 882.9. And what is it then? So if you do everything correct, you are going to get 1854.10 newtons, and that is what? AY. So now we have been able to solve for By, and then we have also been able to solve for AY. Okay. So now we know By and then we know AY. So this question has been solved. We were able to draw the free body diagram, and then we went ahead to solve for the unknowns. Alright. I hope the concept is clear. So now we are going to the next question. Alright. Okay. So now let's move to the next question. Alright, let's move to the next question. Okay, so please hold on. We want to look at the next question. Alright. Such a long question. But we are going to solve it straight away. Alright. So that is our question there. Okay. So a 150 Newton crate rests on a 100 Newton pickup tailgate as shown. Calculate the tension T1, tension T in each of the two restraining cable, one of which is shown. Alright. So now, the centers of gravity of the gate and the crate is J1 and J2 respectively. Assume the crate is located midway between the two cables. Alright. So this problem is asking us to actually find Alright, so this problem is asking us to actually find the tension, alright, the tension. So how can we solve this problem? So just like we did for the first problem, we are going to do the same to this problem. Alright? So the first thing that we are going to do is that we will draw the free body diagram. Okay, because if you don't draw the free body diagram, you will never be able to solve it. You will never be able to solve it. Okay. So now let's consider the tail, the pickup tailgate. Yeah. So let's say I have something like this. Okay. So I have something like this, which represents the pickup tailgate, and then this pickup tailgate is hinged. Okay. So actually, it is hinged to the car. Let's assume that from this direction all the way here is the car. All right. So this part is what we are calling the pickup tailgate. Now the weight of the pickup tailgate is 100 newtons. So that weight is what they are calling the center of gravity. They are calling J1. So it is going to act somewhere here. Let's call that weight J1. Let's call that weight. So this is J1. That's the center of gravity of the center of gravity of the tailgate. Okay. And then the weight is 100 newtons. Now the crate. So the crate is G2. And then the weight of the crate was given as 150 newtons. And then since the crate is since we know the weight of the crate and then the center of gravity of the crate, we can simply say that okay, so the line of action of the weight of the crate is something like this, which will pass through J2. Alright. So let's do it this way. So this line here represents the line of action of the weight of the crate, which is what? 150 newtons. Alright. So essentially what we have here is like a free body diagram, or a free body diagram of the tail pickup, the pickup tailgate. Sorry. Now it is interesting to note that this tailgate cannot be there like that, right? So it's like this tailgate is supported by application of what? A cable. Alright. So it's like I have a cable here, which is helping. It's like the cable is to hold it so that so it's like imagine it's like if I try to open the gate will fall. So to prevent the gate from falling over, the tailgate is there to hold it in position. Alright. So this tailgate, the cable here has got some tension. So this is a cable, right? So now the tension force in the cable will act away. Alright. It will act away from the tailgate. Is that clear? To act away from the tailgate. Now it is interesting to note that so over here so he said that assume the crate is located midway between the two cables. Alright. Then if it is located midway between the two cables, then it means that so if I technically this question, one half of the cable is not shown. There is only halfway, but there is another side of the cable which we cannot see. Alright, we cannot see. Alright, I hope it's clear. Okay. Now the distance all the way from here. So let's add the distance. Okay, let's add the distance. So the distance from here to here is 12 inches. And then the distance to Gen 1 from here is what? So all the way here is 9.5 inches. Is that right? But at point A, the distance from here all the way to the weight is given as what? 2.75 inches. Okay. Now the distance between the weight or the crate and then so let's call it the tail light. Okay, let's say this is the tail light of the car. That distance is 14 inches. Alright? Okay. But then since we are going to look at the tailgate, then we are going to look at all the analysis with respect to the tailgate. Alright? Okay. So let's look at this point here at O. Okay. So looking at O, we can clearly see that this is like a hinge. Okay, a hinge. So for a hinge, so this is O. For a hinge, I am going to get 2 reaction supports along the X. Oh, sorry, let's call it O. So this is going to be OX, OY, right? I'm talking about the reaction forces at O. Okay. Alright. So now I think everything is set. So this is actually the free body diagram. Okay. This is the free body diagram. But we have to be careful because now, okay, let's sum the forces. You get to know what I'm talking about. So first of all, we have to sum forces along the X. Every force in this direction positive should be equal to 0. So let's start. But before we do that, we need to get the angles. Other than that, we will not be able to resolve the tension force. Because as it stands now, it is only OX which is in the direction. But don't forget that we have to convert the tension along the X and the Y. Now how can we do that? We need to get the angle. So let's get the triangle for that. Now let's say that the distance from here to here is 12. Okay, I'm coming. So let's say that the distance from here to here is 12. And then if we know this distance, then we can find this angle, right? So now that distance is going to be 2.75 plus 9.5. Now what is that? So we need to do 2.75 plus what? 9.5. Is that not it? So 2.75. Alright, please, I want you to pick your calculators and let's do this together. Alright, so 2.75 plus 9.5 is actually 12.25. So then this is how we are going to do this. 12.25. So we can use tan, right? So what is the tan inverse? So if this is the angle, what is the tan inverse of, so to get this angle, this is what we are saying. To get this angle, theta, is going to be tan inverse of 12 divided by 12.25. What is that? So tan inverse of 12 divided by 12.25. So we get 44.4. So 44.4 degrees. Is that clear? Alright. So now we can resolve the tension. So plus T cosine 44.4. Is there any other force along the X? No. So that should be equal to 0. Let's call this equation 1. Alright. Now, this is what we are going to do. We will sum forces along the Y. Every force going up should be positive to 0. Is that right? Yep. So let's go back to the diagram. Then we ask ourselves forces in the Y. So 150 is going down, right? Now because 150 is going down, it's going to be negative. And then also OY is actually negative because it is also coming down. Is that right? Okay. So now, what is it going to be then? So actually, it's going to be minus 150. Yep. Minus 100. Yep. Plus T sine 44.4. Yep. Now what do we do? Right? What do we do? So basically, OY. So OY is coming down, so minus OY should be what? Should be 0. Clear? Is there any other force along the Y? No. Alright. So I think we are done. Okay, that's very good. Okay, so now so that is it actually. So then this is what we are going to do. We have to some moments. We have to some moments about a point, so that we can eliminate some of the reactions. So what do you want us to do? Alright, you want us to some moment. Is that right? So we can some moments from either point point A, or we can take moment from O, depending on what we want to do. So we can either take moment from point O, or we can take moment from point A. So let's take moment from point O, alright? Let's take moment from point O. Is that right? So now taking moments about A. Okay, let's take moment about A so that we can eliminate the tension and be able to solve it. Alright, so this is how it's going to be. Counterclockwise is positive, summing moments about A should be equal to 0, right? Is that right? So let's start. This is where we are going to do it. Okay, but we have to know. Okay, I think we'll be able to do it. So now this is what we want to do. What is the distance? What is the distance from? Okay, let me go back to the diagram. So on the diagram, what is the distance from the center of gravity of Jane, the crate, sorry, to where the cable is attached to the pickup tailgate? Interestingly, if this is A, then the distance all the way here, how can we get it? That is what we are looking after right now. Okay, so we all know that the distance from here to here is 14, right? And then we also know that the distance from here is 9.5 plus what? 2.75. So to be able to get this distance, it is going to what? 14 minus what? 9.5 minus what? 2.75. Now if we do this, we will be able to what? To get that small distance, right? Okay. So now let's do it. So 14 minus 9.5 minus 2.75. So 14 minus 9.5 minus 2.75. So that is 1.75. Is that right? 1.75. Alright. So this is what you are actually going to get. Okay. Alright. Okay, so this is what we are going to do. We know that this small distance here is what? 1.75 inch. Is that right? Okay. Alright, so now let's start with the moment. So the moment, this is what we also have to know. Okay, so now we have been able to establish that the distance from this point to this point is what? 1.75 inches. Okay. So now, to take the moment, we know that it's going to what? Counterclockwise. Imagine that you have fixed something here, and then you apply a force in this way. What is going to happen? We all expect that there is going to be a turning in this direction. So counterclockwise. So it's going to be 150 multiplied by 1.75. Yep. And then okay. So now, since we are taking moment about A, the moment of the tension force about that point is 0. So we don't need to bother. And interestingly, the line of action of OX will pass through A, right, to pass through the horizontal direction. And since the line of action of O passes through that point, then the moment is also 0. It is interesting to know that we would, so let's look at the 100 Newton. That one is 2.75, we know. And then it's going to what? Looking at the direction, you can see that it's going to clearly clockwise. So it's going to be clockwise actually. So minus 100 multiplied by what? 2.75. Is that right? Which is clockwise. So that's why it's minus. Because we are saying that anti-clockwise should be positive. Is that right? Okay. Now we need to do OY. That is the last one. In fact, OY is also going to be negative because it is clockwise. But what is it? OY is going to be multiplied by what? So the whole of the distance up to A, what is it? So 9.5. So 9.5 is here, and then you add it up to what? 2.75. Now what is that? So 9.5 plus 2.75. 9.5 plus 2.75. What is that? So that is 12.25, right? So please take your calculators and let's do it together. 9.75 plus 2.75, that is 12.25. Okay. So that distance which the OY is getting is so it's going to be OY. Alright, so we don't know, so just say OY. So OY multiplied by what? 12.25. Okay. Now this will be equal to what? Let me write it all. This will be equal to 0, isn't it? Now, with this, what do we do then? So we can solve for OY, right? So what then is OY? Alright, so OY can be solved as so first of all, let's do this. 150 multiplied by 1.75 minus 100 multiplied by 2.75. That one is minus 12. So minus 12.5. Okay, let me do it this way. Let me take my time. So 150 multiplied by 1.75 minus 100 multiplied by 2.75. That one gave us minus 12.5. And now we are saying that minus 12.25 OY is 0. Is that right? So therefore it means that OY is going to be 12.5, which in other words means we are sending it here. Then we divide by what? 12.25. So what is 12.5 divided by 12.25? So 12.5 divided by 12.25. So in fact that is going to be 1.02 newtons. Alright. And then to get now since we have OY, then what is it? So we can go back and put this into, okay, let's call this equation 2. And the moment, let's call it equation 3. So you can actually go back and put OY into equation 2, which is going to what? um so minus 150 minus 100 plus t sine 44.4 minus OY was 0, right? So this was the equation. But now, if we solve for t, so t sine 44.4 will be equal to 150 plus 100 plus OY, which is 1.02. Is that right? So that t, which is the tension, will be 150 plus 100 plus 1.02. Okay, so I'm having some challenges with the calculator. So please, I want you to pick your calculators and let's do this together. So it's going to be divided by sine 44.4. So that t is going to be 150 plus 100 plus 1.02 divided by sine 44.4. So the tension force is actually 358.77 newtons. So that is the tension force, okay? That is the tension force right there. Okay. So that is the tension force for you. Therefore, we can go back and solve for OX. So OX from here. So OX will just be what? Okay, let me bring it down. So OX will just be what? Minus T cos 44.4. So OX will be what? Minus T cos 44.4. Which is what? 358.77 cosine 44.4. And what is that? So we are going to get that is 358.77 cosine 44.4. So 256.33. 256.33. So minus 256. So the minus sign here tells us that OX is actually going inside and not coming outside. So OX is going inside. And then it is what? 256.33. 256.33. Alright, so that is it actually. In fact, this question was not asking us about the the question was not asking us to find the tension force. The reaction force. But you have to use it in order to find the tension. Alright, and the tension force is what we calculated, and then we were able to get 358.77. So to the nearest whole number is going to be 359, or let's say approximately. So the tension force is approximately 360 newtons. Unless depending on the question, what the question asks you to do. Alright. Okay. So now we have the tension force. So this question has been solved. Actually, this question has been solved. All right. Okay. All right. So now, I want us to look at. So now, in fact, we have been able to look at equilibrium of rigid bodies. All right. There was a last question I wanted us to solve. Okay, maybe let's look at that one. But I think because of time, I want to look at internal forces. But the concept is the same for every question you are going to look at in the equilibrium of rigid bodies. Everything is the same. You only have to draw the free body diagram. Okay. So I want us to look at internal forces and internal reactions. Internal forces and internal reactions. And then we will look at internal torques. All right. So I want us to look at internal forces. Internal forces. So let's look at internal forces, please. Let's say I give you a question like this. All right. Now let's say you have been given a question like this. Okay. Let's say you have been given a question like this, and then all right. So I hope everybody can see the question. Now with this question, we are to determine the axial forces. So axial forces transmitted by cross section in intervals AB, BC, and CD. All right. Okay. So for this question, we need to look at internal forces and then internal reactions. All right. So then, how do we do this? All right. How can I how can I solve this problem? Okay. So now the first thing to do is to actually look at what we call the internal forces. So you will start by cutting the sections, okay? Alright, so this is how you are going to do. So you introduce a section or a cut. Alright? Now, if you introduce a section or a cut, now let's think about it this way. Let's say you have bread. Okay, let's say you have bread. Let me put it this way. Let's say, assuming this was to be some bread, and then you divided the bread into two, what are you going to see? So you will see that this portion which you have cut will be here. Alright? And then you will see that this is A, and the force acting here is still what? Say 60. Okay, let me do it well. The force which is still acting here is 60 kilonewtons. But then you will realize that since you have cut this portion, then this portion will be separated from the other part, right? Okay. Now, since this portion is separated from the other part, it tells us that there is something happening internally. Alright? Picture this as something like this. Okay, let's say I decide to cut. So it's going to actually cut through a certain section. Alright? So looking at it internally, you see that the portion, there is a section, like there is a plane which cuts through like that. Alright? So we are calling that, let's say, since I introduced the cut between A and B, then I'll call this FAB. That is to say, the force or the internal force in member AB. And what is the direction? In fact, the direction of that force will always act in a direction which will cause equilibrium. Alright? So if you look at this carefully, what you have here is FAB. What does it mean? It means that if I stand between A and B, and then I introduce a cut, then because of the cut which I have introduced, then there is an internal force between A and B. That is essentially what it means. Okay. Alright. And the direction of the internal force will always make sure that it will balance the forces. What do I mean by balancing? Now, if you do a check on this by summing the forces, so let's okay. So then what is FA anyway? So FA is actually going to be FAB, sorry. So FAB will be 60 kilonewton from equilibrium. Right? Why is FAB 60 kilonewton? FAB is 60 kilonewtons because if I sum forces, don't forget that if you sum forces to 0, you realize that the 60 in this direction will be minus 60, and the 60 in this direction will be plus 60, which is 0. If you sum forces and it is 0, what does it mean? Do you remember what we just did? We said that summation of forces should be 0 for equilibrium. Therefore, it is in equilibrium, so it's correct. So we are done with the first part. FAB is 60 kilonewtons. Is that right? Now we will go to the next section. Now we are going to B and C. Alright? So maybe let me bring FAB downwards. Okay, so FAB is done. Alright. So then let's look at FBC. So for FBC, again, we are going to stand between B and C. And then we will cut. So we are going to cut through B and C like that. Okay? Now when I introduce a cut, now this is what is going to happen. So assume again, let's say you have a bread and then you have taken a cut. Alright? Let me send the first part up. Okay. So because you have introduced a cut, this is what you are going to get. So it's going to be the whole of this region up to where you have what? Introduced the cut. Is that right? Portion A is here. And what is it? 60 kilonewton. Right? And then portion B is here. So portion B is here. And the force acting at B is what? 80 kilonewton. Now we have taken a section, which is what? Between what? Between B and C. So we can't draw B because we can't draw C, right? We cannot draw C because the section has taken or is passing through B and C. Is that right? Alright. Okay, so what does it mean? In fact, there is a force which is so if you cut between B and C, there is an internal force which is actually between B and C. But this internal force, if we want to really show this internal force, then we have to look at the forces. So this is 60 kilonewtons, this is 80. But let's sum forces, alright? Every force moving in this direction is positive. Let's do that and see. So 60 kilonewtons is minus, and then 80 kilonewtons is what? Plus. Is that right? So we are going to get what? 20. Is that right? So what this means is that the summation of all of the forces acting on this body, right now, all the forces acting on this body is what? 20. So for this body to be in equilibrium, then I need to attach an internal force. And that internal force will be in a direction so as to bring equilibrium. And so what is that? So that is going to be a force which will act in this direction. So FBC. So all what we are trying to say is that if FBC is minus 20 kilonewtons, then the whole of this will be in equilibrium. Alright? So that's all what we are trying to say. I hope the concept is clear. So minus FBC, FBC is minus 20. So now we know FAB, and then also we know FBC, right? So now, what else can we do? Okay. So we will come here, but this time around, we are going to cut between C and D. Alright? Okay. Okay. So. Okay. Yeah. I think we are done with this part. Let's move on to the next part. So yeah, C and D. Now it is interesting. So it is interesting to know that when we get to the last portion, which is between C and D, I can either use this portion here to find the force in CD, or I can use the whole of this to find the force in CD. Now let's start with the difficult one, and then I'll show you the simple one. So let's use the whole of this portion to find the force in member CD. Let's do that and let's see. So if we try the whole of this portion, look at what we are going to get. So like introducing a cut here. Yep. Then I have a force here, which is what? 60 kilonewton. Right? Now, so A, B, which is 80 kilonewton, and we have to indicate C. So this is B, that is C, and then yeah. So A, B, C. So C is 50 kilonewton. Alright. So then you begin to ask yourself. So if I have 50, so the direction is very important, because don't forget that a force have three qualities: the magnitude, the direction, and then the line of action of the force. Now, interestingly, if we look at it from this angle, so let's ask ourselves, summation of forces, every force here, alright? So let's sum the force and see. So minus 60 plus 80 minus 50. And what is that? So minus 60 plus 80 minus 50. What is it going to be? Alright. So it's going to be, so let's pick our calculators. So minus 60 plus 80 minus 50. So that's minus 30. Wow. So if you sum all the forces, you are getting minus 30, right? This is telling us that since the sum of all the forces is minus 30, then I need a force which will make it be in equilibrium. Then that force should be against minus 30. So minus 30 would have acted in this direction, right? Therefore, to make all the forces zero, then I need a force going this way. Which is what? F so FCD should be what? 30. Interesting. Why is FCD 30? Because the sum of all the other forces is minus 30. And so we just need a force which is 30 kilonewtons, which will just act in the opposite direction, and then it will make it what? Zero. That is to say, don't forget that for equilibrium, summation of forces is zero. That is what? Equilibrium. That's what we said initially. Is that right? Okay. But interestingly, let's go back. Oh. So you see that interestingly, we could have used the short portion to do that, right? All right. Look at this carefully. So look at this carefully. You see that if I were to use the small portion, then you can see that let's say this is the cut, and let's say this is the small portion, and then here was 30 kilonewton, and this was D. So for equilibrium, we just have to attach another 30 here. Right? Because if I have this 30 and then I have this 30, it's going to what? Zero. Is that right? So you realize that in both scenarios we can actually solve and get the internal force. All right. So now that we have the forces, we can calculate the stresses. So determine the stress at each interval if the bar has a constant cross-sectional area of 100 centimeters squared. Is that right? Okay. So now let's finalize our answers. So FCD is 30, and then FBC is minus 20, FAB is 60. So the stress, or let's say the normal stress in AB is going to be the force in AB divided by the area. Now it says that the area is actually constant. So it means that the area will not change. Is that right? So now the area will not change. But we just have to change the force. So for FAB, so the stress is going to be the force, which is what? So let's go back and look at it. FAB is 60 kilonewton. So 60 kilonewton, right? Divided by the area. And what is the area? So the area is 100 centimeters squared. So 100 centimeters squared. Alright. So it's going to be 60 times 10 to the power 3, or divided by 100 times 10 minus 4. Don't forget that centimeters is 10 to the power minus 2, right? Now if I do everything correct, the stress is going to what? So let's make our calculators. 60 times 10 to the power 3 divided by 100 times 10 to the power minus 4. So that is going to be 6, 0, 0, 0, 0, 0. So the zeros are 1, 2, 3, 4, 5, 6. So in engineering, we can write this as 1, 2, 3, 4, 5, 6. So 6.0 megapascals. Alright? Okay. So that is the force actually. Alright. So that is the force. Sorry, the stress. Sorry. And then sigma is sigma. Let me go and check. Yeah. BC. BC. So it's going to be the force in BC divided by the total area. The force in BC, what did we get? We had minus 20 kilonewton. Divided by 100 times 10 minus 4. And what is that? So 20 times 10 to the power 3, 100 times 10 to the power minus 4. So that is also going to be, sorry for that. So that is going to be 2, 0, 0, 0, 0, 0, 0. So in engineering, you can see that this is minus 2.0 megapascal. So now if I have a stress which is positive, we call it a tensile force. But if it is negative, then we call it compressive. Alright? And then sigma CD. Alright? So sigma CD is FCD divided by the area, which is 30 kilonewtons. So it's going to be 30 into 10 to the power 3 divided by 100 times 10 minus 4. So that is again. So basically you are going to get 3.0 megapascals. So that is the stress, alright, which is what? Tensile. Alright, tensile stress. And the negative is the compressive stress. Alright, so we have been able to find the force in each member, right? Maybe let's take one more example. Okay, let's take one more example. Alright. Okay. So we have this question. Alright. So this is the last problem. Internal forces. I will look at internal torques, and then we will look at the shear force and the bending moment. I think many people are waiting for that. So from here we are moving to internal torques, and then I'll move straight forward to the shear force and the bending moment diagram. Alright, so let's solve this problem. So we are going to use the same concept, right? We are going to use the same concept. But just that this time around, if you look at it critically, you see that we have got a support reaction over here. That's all. So the difference between the first example and this example is that for this one we have got a support reaction. That's all. All right. So let's look at this one. Okay. Okay. So now let's go straight forward. If I draw the free body diagram of this, what is going to happen is that because there is a support reaction here, this reaction is coming from the wall. So the wall will try to give him a reaction here. That's all. So now this time round, we will have to include a reaction. And this R reaction is coming from what? The wall. Alright? It is coming from the wall. Okay. So let's move forward. Summation of forces along the x, every force moving in the direction is positive to 0. What do we have? So R minus 75 plus 100 minus 50. What is that? So that is equal to what? 0. Right? So therefore R is going to be what? If you solve for R, minus 75 plus 100 minus 50. So minus 75 plus 100 minus 50, that is minus 25. Yes? Okay. So minus 25 kilonewton. Right? Okay. So basically what is actually telling us is that okay. Alright, so no, sorry. I think there's a mistake here. So minus 75 plus 100 minus 50 will give us 25. Or minus 25. So that R will be 25 kilonewton. So that is R for you. So now we can go back and replace the force here by what? 25 kilonewton. That's all. So that is all for this one. We just have to cut again. Alright. So let's quickly do this. I'll cut between here. Now if I cut this, it will look like this. So this is 25 kilonewton. Now the force here is what? FAB. And what do you think FAB is going to be? But FAB must counter it with 25 so that it will be in equilibrium. So in other words, this force which is FAB here, here is going to what? 25 kilonewton for equilibrium. Is that right? For equilibrium. That's all. That's all. Now, if I want to get FBC, I'll come and stand between B and C and I'll cut. Now, if you cut, should I draw it again? Yes. Okay. So for FBC, the force comes here, 25 kilonewton, and then as usual, you have this, right? Now interestingly, here is going to be so this time around here is E, but then here is B, and then here is, so this is where we have taken the portion, right? Okay. So now we have this. So this is the section, right? But don't forget that there is a force which is acting at B. And that force is having a magnitude of what? 75 kilonewtons. Okay. So now, looking at it carefully, you want to ask yourself, what is the force needed here for equilibrium? It is interesting to know that now if I sum the forces here, positive in the direction, you know that this is what 25. Okay. So 25 minus 75. And what is that? So 25 minus 75, that is minus 50. Clearly speaking, it means that the summation of the forces is minus 50. So if I need a force which will cause it to be in equilibrium, then I need that force to be in the positive direction. Alright? So in other words, that force must come here. So it means that FBC is 50 kilonewton. You can clearly see that if I have 75 here, then if I add 25 and 50, if I have 75 in one direction, if I have 25 and 50 in the opposite direction, then they will add up to 75, which will make it what? 0. So now we know that FAB is 25 kilonewtons. And then FBC is 50 kilonewtons. Right? Yep. Okay. So now we have to look at the last part. Okay. So you cut here. Now interestingly, what do you have? Okay. So I don't need to get the large portion here. I can use just that small portion. So if I cut through, and then I have this. You see that the force 50 kilonewton is acting here. Therefore I just need this force here. Right? Therefore FCD without doubt must be what? 50 kilonewtons. That's all. So that is how this can be simple and straightforward. So FCD is 50 kilonewtons. Alright. Okay. So that is FCD for you. Now so we are done with the part which says we should calculate the axial forces. So if it says sketch the internal force diagram for the shaft. Okay. So for the internal force diagram, it's simple. So I can sketch something here. Okay, let me bring it down. Alright. So then I have this. Okay. So now if you look at the profile of the shaft, from the beginning there was a force which was 25. Okay. So now let's look at it carefully. Wait. So FAB is going to be compressive, right? But FBC is going to be what? Tensile. And then FCD is also going to be compressive. All right. So in other words, FAB is actually minus. Why is it minus? It is minus because of the direction. Okay, it is minus. Similarly, FCD is supposed to be minus because of the direction. This is the section, and it is acting towards the section. Now, if it is acting away from the section, then that is a tensile force. All right. So now the top diagram is going to be pretty much simple. So this is how the top diagram looks like. So basically, you come down. That is to say the compressive force. You come down 25. So minus 25. And then you are here. And then you go up. So this is between A and B. And then when we were at B and C, the force was what? FBC, which is 50, which is tensile. So that one will send you up. So actually you go up. But because this is 25, this is also going to be 25. So that this will be 50. So here is what? 25. And then you were constant out until you came to, so this is B. And then at point C, you became negative again. But what is it? Minus 50. So it means that it came back to minus 50. Don't forget that this is 25. So it will come to 0 first. So this line is the 0 line. Before it comes to minus 25. So minus 25 minus 25 you get minus 50. And then you come all this way here. So this is what we call the axial force diagram. Or the internal force diagram actually. Okay. So this question has been solved. Alright, guys. Now before we move to the shear force and the bending moment diagram, I want to solve one question on internal torques. Alright. So now let's look at internal torques, and then we will look at the bending moment and then the shear force diagram. All right. Okay, so let's look at this problem. All right. So let's solve this question. All right. Let's solve this question for internal torques. and then I'll solve one question on shear force and the bending moment diagram. All right. So there are several questions, but we cannot solve all of them right now. So all what you have to do is trying to solve most likely questions for your understanding. All right. So now this is what we have. And then in this question, you can see that we have been given a gear, all right? Sorry, a motor. And the motor has some couplings, all right? Now, basically, if you look at it carefully, you will see that, so this is the motor. And this motor is supplying some torque, all right? And the torque the motor is supplying is what? 500 Newton meter, right? Okay. And now this torque is being supplied. But then if you look at it, you will see that at any point in time along the shaft, there is a gear. So you can see that the coupling is at B. So the coupling is at B, and then you will see that the shaft. So the whole shaft is connected now from A all the way here. That is the axis of the shaft. So we can actually look at this problem as a shaft. And then instead of looking at the gears, we'll be looking at the torques supplied by the gears. So if this is say point A, and let's say this is in fact there is nothing at point A because A is attached to the shaft. The motor, sorry. So the actual turning starts from B because A is the point which is on the shaft. So relatively assume that point is taking that same torque from the motor. So then we start from B. All right. Now if we start from B, these are the torques. So now it says that the torques, so the torques removed at gear C, D, and E are 100, 150, and 250. But then before we can find B, okay, so this is C, this is D. Okay, let me bring it down. So this is what I'm trying to say. So let's say that we have the shaft here. Okay. Let me bring it down here. This is the shaft. Oh, sorry. So the shaft is here, and then this is B, this is C, and then there is point D, and then there is E. All right. Okay. So now what are we going to do? So we need to understand. Okay. So now if the motor begins to turn, okay, let's look at it this way. If the motor begins to turn, then as the motor turns, gear C is going to rotate. This is also going to rotate. So all these are like gears which are actually rotating, right? So to counter it, the coupling at B will need to provide a counter torque or moment. Alright? So basically that is what is happening. Okay. Now let's start. So we want to find the torque at B. More or less, sorry. So it looks like a reaction. Okay, the torque at B. So let's call this torque at B. Let's call it let's say TR. Okay, reaction torque. Now it says that the torque removed from at gear C, D, and E is what? 100, 150, 250. So 100, 150, 250. And these are all in what? Newton meter. Alright? Okay. So then how can I solve and get the internal torques? Okay. So how can I solve and get the internal torques? Now to get the internal torques, I need to cut. So you see that what? Determine the torque transmitted by the transverse cross section in intervals BC, CD, and DE. And then sketch a torque diagram. And then in what section does the maximum shear stress occur? Alright. So then let's look at it together. Okay. So let's look at it. We can clearly see that for this problem, we have to sum torques, not just forces, because everything here is what? Torque or moment. So we have to sum torques to be 0. So summing torque to be 0, but we need to choose a convention. So we can say that clockwise is positive to be 0. That's a convention. So TR is going to be in a direction which is going to oppose no, I think I have to do it this way. So this is what we are saying. C, D, E are attached to the shaft. So they are going to rotate with the same direction. But then this portion is going to be counterclockwise. Okay, so I think it's going to come this way. Sorry for that. So it's going to oppose it, alright? So it's going to actually oppose it. And what is that? So it's going to be TR. So TR is going to be minus because it's going to be counterclockwise. Then I have plus 100 plus 150 plus 250 should be what? 0, equilibrium. So essentially TR is essentially going to be so TR is essentially going to be 100 plus 150 plus 250. And what is that? So 100 plus 150 plus 250, that is 500. So in other words, what this is trying to tell us that the motor is supplying 500 Newton meter, and this same 500 Newton meter is supplied exactly at the coupling. Alright? This is the coupling. Alright? So now So now we need to find the internal torques, the torques which are in between. So starting, so now we know. So now we know that TR is 500. So the same thing, we are going to take a section and cut, alright? But for this one, if I take the cut, instead of summing force, I will sum torque. So you are going to get something like this. So TR is going to rotate it in this sense, but for equilibrium, then we expect that for equilibrium, the internal torque will actually act in an opposite direction. Okay? So if this guy is coming this way, okay. So what we are trying to say is that if this will rotate it this way, then this one will rotate it in the opposite way. Okay, no, let me take my time and do this. So what we are trying to say is that if this will rotate it okay. So if this guy will rotate him in that sense, then there is the opposite. Okay, so if this is going this way, then this will come to counter it. Alright? So if this goes this way, this will try to counter it. And so basically the torque in what is it? BC, right? So the torque in BC is exactly 500 Newton meter, right? So the torque in BC is exactly 500 Newton meter. Okay. But the direction is very important because torque is like movement, so you have to specify the direction. So if this one is to set it in anti-clockwise, then we can say that the torque will go clockwise. Alright? Why is it that? Because if we go that way, then it's going to cause equilibrium. Right? Okay. Now, okay. And then, so we are done with the first part. Now to look at the second part, we will look at CD. So again, we will come and take a section here. So if you look at the section, so it's like you have cut all the way here up to C. So then, so you are going to get something like this. And then, don't forget that there is 500 Newton meter. And then, at C, there is 100. So at C, there is 100. Right? Okay. And then at D, no, we are not at D yet. So we are between C and D. So if you take a section here, then that force to cause equilibrium. Okay. So now let's ask ourselves. So now C is what? 100. So C is 100, and then this one is what? 400. So 500, sorry. So if I have 500 in this direction, and then I have 100 in the opposite direction. Then for equilibrium, it means that I need to also get what? 400 in the opposite direction, right? So in other words, this torque, which is TCD, let me check. Yeah. So this torque, which is TCD, that is between C and D, must be what? 400, right? For equilibrium. Why is TCD 400? Because if this is 500 and then I have 100 which is in the opposite direction, so I have 100 which is in the opposite direction. Therefore, it means that I need TCD to come again in the opposite direction. Why? So that if I add 500, if I add 400 to 100 in the opposite direction, when I add them together, then it means that I have what? 500. So all the time, summation of torque is 0. Always. Summation of torque is 0. Always. Alright? Now finally, let's look at between D and E. So between D and E. Now interestingly, the last portion is actually D. So when you get to D, E. So between D and E, in fact, all these are bearings. Okay, all these are bearings holding the shaft. Now, if I get to point E, this one, I don't need the whole of the shaft. I just need only that portion, right? Because I know the torque at E, which was what? 250. Okay, so now I know that TCD is 400. Okay. So interestingly, the force in DE will also be what? So the force in DE, so that's what we are after. So but then we don't need to have we don't need to draw everything, because now let's say this is E, and then I know that the force in DE is what? 250, right? So since it is 250 Newton meter, so since it is 250 Newton meter, then all what I need to do is what? So I will just clear here, then I will say that okay, so this one is 250, therefore the other force which will actually cause equilibrium must also be what? 250, but it will act in the opposite direction. Alright? So then that force must be what? 250. Alright? So let's call that TDE. That is the torque in DE. So essentially TDE must also be what? 250 Newton meter. Alright? Okay. So the torque in section DE is also what? 250, right? Okay. So, but that is how you solve questions like this. Now it says that in what section does the maximum shear stress occur? So how do you calculate the shear stress? In fact, the shear stress will actually be the torque times the radius divided by the polar moment of inertia, which is G. But in this problem, it was not given. But if we have the same, so if we have the same radius and we have the same polar moment of inertia, then the torque is going to be maximum in section CD. So the torque is going to be maximum from C to D, because that is the BC rather. It is BC because BC is 500 Newton meter, right? So the maximum torque is experienced in BC. All right. Okay. So now time is fast spent. Time is fast spent. I want to look at the last part for today, which is the shear force and the bending moment diagram. But there are several questions. There are several questions of which we cannot solve everything here. All right. So I want us to look at the shear force and the bending moment diagram, and then we can close for today. And then what I will do is that we have to create another time, and then we will look at the second moment of area, and then we will also look at the stresses. Okay, we have to look at the the axial stress, the Poisson ratio as well. So basically what I'm trying to do is that I'm going forward and I'm coming back, so that you get a balance of everything, right? Okay. So then I want to teach you how to draw the shear force. Okay, so let me write it like this. So shear force diagram and bending moment diagram. So SFD and then BMDs, alright? Okay. So this is a simple question, and then let's say you have been asked to draw the shear force and then the bending moment diagram of this question. How can you solve this question? How can you solve this question? Let's say you have been given a problem like this, and then you've been asked to find or draw the shear force and then the bending moment diagram. Okay. So this will be the last part one. I'll solve two questions here. So this will be the last part one question, and then we'll end the tutorial for today. Okay. So from this question, so this is how we normally draw shear force and bending moment diagram. To be able to draw the shear force and the bending moment, there is a convention which you need to know, and I want to show it to you right now. Alright, so this is the convention that you have to use. This is the convention that you always have to use. But I don't encourage you to memorize everything. I only want you to memorize one. Just memorize only one of them. So you can either memorize the positive convention or the negative convention, right? So if you want to memorize the positive convention, you can take it. If you want to look at the negative convention, you can also take that one. But I always advise my students that please memorize the positive convention, because that is mostly the standard. So whenever you have a section, so this is what it means. Whenever you have a section W of X, alright, W of X can be any distribution of force at all, right? If you take a section like this, the shear force, which is in positive shear, will be V, and this will also be V, alright? And then the bending moment will also be positive in this direction, and then in this direction. Now again, you don't need to write the two of this. So whenever you are drawing the shear force and the bending moment, what you have to do is that with this convention, what do you have to do? You have V and then you have M. So the shear force and then the bending moment. Alright? Okay. So now this is how we are going to solve it. Okay. Alright, so to be able to draw the shear force and then the bending moment diagram, what do we do? Alright, so let me move on. Sorry. So first of all, I will take a section. So already I have done that for you. I will take a section between A and B. Alright. But in fact, this one, it has been done for you. But I want us to do. So the first thing to do whenever you are given a question like this is to, number one, solve all reactions. Okay, that is the first thing to do. Solve all reactions. Alright, so in fact, you cannot solve the reaction without drawing the free body diagram. So please, number one, draw the free body diagram. So draw the FBD, that is to say the free body diagram. Number two, find the reaction forces. So find the reaction forces. So after getting the free body diagram and drawing finding the reaction forces, in fact, that is where you actually begin. Alright? That is where you actually begin. Okay, so this is where we are going to start with. So now we have been the reactions has been given to you already, but I solved it. So I want to solve it again with you. Alright. Okay. So I will not draw the free body diagram because now this is a pin joint and then this is a ruler. So I have a pin supports two reactions. Okay. So there is a reaction AX and then what? AY. Is that right? Okay. But it turns out that AX will be 0 because there is no force along the x direction. And then let's call this one. Let's call this D. Alright. So RD. Okay, so let's call it RA and RD. I just want to show you how they came about. So first of all, summation of forces. So some forces in the Y, every force going up is positive to 0. So RA plus RD. What else? Minus 14 minus 28, right? Should be what? 0. Is that right? So RA plus RD is what? 14 plus 28. And what is that? So that is going to be, so 14 plus 28 is going to give us what? 42, right? So let's call this equation 1. And then we are going to some moment. Okay. So please, what we have done here is that to be able to solve any question under shear force and bending moment diagram, you need equilibrium of rigid bodies. Very, very important. It is very, very, very important. If you don't understand equilibrium of rigid bodies, you cannot solve. Equilibrium of rigid bodies. That is the reason why I did it with you in the first part of the tutorial. So for those of you who did not watch that part, please you need to watch that part. Okay. So now we can sum moment at point A. So summation of moment about A. Every moment which is clockwise is positive to 0. Alright? That is the convention. So you can either choose so the choice is all yours. Alright? You can either choose clockwise or anti-clockwise. Is that clear? All right. So now let's start. So 14 kilonewton multiplied by 2, and then it's going to what? Clockwise. So, alright, let me bring it down. So 14 multiplied by 2, right? And then 28 multiplied by what? 5, right? So 28 multiplied by 5. And what is that? So 28 multiplied by 5. Okay. And that is also clockwise. So plus 28 multiplied by 5. And then finally, RD multiplied by 2 plus 3 plus 2, that is what? 5 plus 2, that is 7. So 24 multiplied by 7. But what is that? That one is going to minus. Oh, sorry. We don't know, so it's not 24. It's RD multiplied by 7, and that is counterclockwise, so minus. So 7 RD. Is equal to what? 0. Is that right? Okay. So now 14 multiplied by 2 plus 28 multiplied by 5, which is what? 168. So basically, RD is going to be 168 divided by 7, and 168 divided by 7 is 24. So that is where the 24 kilonewton is coming from. It is not magic. Alright? This is not magic. Now, since we know RD, then RA is going to be simply what? RD minus what? 42. And what is that? Sorry. 42 minus RD, which is 42 minus 24. And what is 42 minus 24? 18, right? Okay. So RA is what? 18. Agreed? Okay. So RA is actually 14. Sorry, 18. Alright? Okay. So in fact, this is where you even begin solving the question. Now you know RA, and then now you know RD. So 18, 24. Okay. So now we are about to solve. We know where all these values are coming from. Okay. So now we will take a section, a cut here. Alright? And when we cut it, since the distance between so let's say the distance from A to B is what? 2, right? So if we cut between A and B, it's going to be something like this. So it's going to be something like this, okay? And then the reaction at A is 18 kilonewton. But this distance from here to here, we don't know because we just took a section. So we can call that section X, where X is varying from X equals 0 here all the way up to what? X equals 2. So if you are between here, if you are within the cut, then the value here is what? X is such that X is between 0 and 2. So less than 0, greater than 0, less than 2. And that is where the cut is actually at. It's actually between 0 and 2. So then you introduce. So this is where you are going to introduce what I taught you here. So using the positive convention, since we introduce the cut to the right here, it means you are going to show what is here. Alright? But if the cut was somewhere here, you will show the one on the left. So now for this one, because the cut is here, you are going to show the shear force is coming down this way. And then the bending moment is going to come that way. So now this is M of X, and then the shear force is V of S. Alright, so we have V of X, and then we have M of X. So M of X and then V of X. Okay. Now we are going to take this body as a deformable body, some forces and some moments. Alright. So it means that considering the shear force, so we are going to some forces actually. Summation of force, every force going up is positive should be 0. So you can say that 18 minus V of X is 0. So that V of X is what? 18. That's all. It tells us that the shear force from 0 to 2 does not depend on any distance at all, and it is a constant. Alright? Okay. Now let's look at the moment. Let's look at the moment. So for the moment, we are going to some moment again about X. So this is X. So we are going to some moment about X. Okay, let me do it this way. Summation of moment about X counterclockwise should be positive, right? Should be 0. Equilibrium, isn't it? Okay. Now Ms is positive because it is going counterclockwise. So the choice is yours. Whether you use clockwise is positive or anti-clockwise is positive, right? The choice is yours. Alright. So Ms, and then this 18, what is the line of action? It is going this way. The force is creating a moment which will go in the clockwise direction. So it is minus. So 18 times what? X. So it means that M of X is what? 18x. Now, interestingly, what this means is that the moment function itself is actually a function of x. Okay? The moment is a function of x. Think about 18x as a straight line. Think about this as a straight line with slope of what? 18. And then x is going to change. Right? But since x is between, okay. So don't forget that the cut that we have done is actually x between 0 and 2. Okay? Alright. So it means that the minimum moment will occur at x equals 0 and the maximum moment will occur at x equals 2. Alright. So we are done with the first part. Now, after doing the first part, we are going to repeat the same thing, and then we are going to start between B and then C. Alright? And then we will introduce a cut. So that is the one that he has said 2. So if you introduce a cut here, right? Don't forget that this is 2. So by the time that you get to B, you are already at x equals what? 2. So then between B and C is x equals 2 till you get to x equals what? 5. Alright? Now we are going to repeat the same step which we did. Okay? We are going to repeat the same step which we did for the first part. Okay. So now, since the section is here, we will bring every force. Okay. We will bring every force. Now this is how it's going to be. So 18 kilonewton is here. Alright. And then so 18 and then 2 meters we have 14. Okay, so the distance from here to here is 2 meters and then we have 14 kilonewton. Alright. And then between 14 and then what? 28. Okay. So now this one we don't know. But we know that so we have taken a section here. Okay. So let's call the distance from here to here x because we don't know. So now this is what we know. We know that this is x. But the small distance here is what? X minus 2. Because if the whole of this is x and this is 2, then the small distance here is what? X minus 2. Alright? Okay. Alright, so now this is 2. This is x minus 2. Alright. So then this is what we have here. Is that right? Okay. Now we are basically going to do the same thing here. So since we have taken a section, sorry for that. Okay. Since we have taken a section, then we can say that the shear force will come down and then bending moment will go up, right? Okay. Now let's sum forces. So again, the shear force. Okay. So summation of forces, every force going up should be positive is 0. So 18 minus 14 minus the shear force should be what? 0. So that the shear force, so what then is the shear force? So the shear force is what? So the shear force is 4 kilonewton. Alright. Now, with the moment, right? With the moment. So we are going to some moment, isn't it? Alright. Again, summation of moment about x is 0. So clockwise is positive, right? So then it's going to be what? Alright, let's say that anti-clockwise. Okay, anti-clockwise is positive. That doesn't really change anything. So I have m of x. That one is already anti-clockwise. Now we are summing moment about the x, alright? Okay. Now 14, so what is the distance? The distance from here to here, 14. So plus what? 14 multiplied by x minus 2. Is that right? That is the distance to the x section. Again, with this one, it's going to be for the 18 guy, it's going to be what? Clockwise. So minus 18 multiplied by what? X. Yeah, x. Sorry. Is there any other force we have not looked at? Alright. Okay. Alright. So now so we have the shear force, and that is what we have here. Alright, so with the moment should be equal to 0, right? Okay. Now So then rearranging, we can say that, so minus 14x plus 28 plus 18x, right? So that m of x is 4x plus 28. Wow. Isn't this concerning? It means that the 4x plus 28 which we have here can be thought of as some straight line. So it means that the moment function from x equals 2 to x equals 5 was a straight line. Alright? Means that the moment function was a straight line, but then the straight line was having an intercept of what? 28. Okay, we are going to plot it, but at this point we just want to find the shear force and then the bend moment, so that once we start drawing, it will be easy for us. Now the last part, so don't forget that the x in this case is from 2 to 5. Now the last one. So the last one is this section. The one that is at 3. Which is what? Between so it's between 5 and 7. Don't forget that the distance from here all the way here is 5. And then all the way, if you add 2 to it, is 7. So if I take a cut at the 3, so if I take a cut in this section, then it's going to what? 5, 7, right? So for this one, x, okay. So for the third one, let me draw that one. So basically for that one, we need to draw everything. And then we will, so we are going to draw everything and then we will cut this part, okay? Or, okay, let me just do that. For the sake of some friends, let me just do that. Let's cut this portion, alright? And then what we are going to do is that we will look at all the forces up to this point. So we have 18, 14, 28. So it looks like something like this. Eighteen, 14, 28. Alright. So maybe let me come down. So 14 28, right? The distance from here to here is 2. And the distance from here to here is 3. But now, so let's say this is A, B, C, right? So yeah, A, B, C, 2, 3. Okay. So you see, if I take a section here, then for that one, it means that I am not, okay, again, let me measure my distance, which is x. So all the time, that force, so if I take a section x, then the distance x will be from 18, from the first force all the way to where the section is. Is that right? Okay. Now, now let's look at it. So for this one, it means that the shear force will come down and the bending moment will go that way. That right? All the time. Alright. So now, again, summation of forces, every force going up is positive to 0. 18 minus 14 minus 28 minus the shear force is 0. So the shear force is what? 18 minus 14 minus 28. Let's look at calculators. What is that? So 18 minus 14 minus 28. What is that? Okay, so that is going to give us minus 24. Okay. Alright, so the shear force is going to give us minus 24. Sorry. Okay. Again, let's sum moment to 0. Counterclockwise is positive. So that is going to what? So first of all, 18 multiplied by x. But that one is what? It's going to go in the clockwise. So minus. So minus 18x. Alright. Now, if this distance is x, from here all the way here is going to what? X minus 2. So 14 times x minus 2. But then the moment is going to cause a rotation, which is what? Counterclockwise about this point. So 14 multiplied by x minus 2. And then finally, so we have 28. So plus 28. So if the whole of this distance 2 plus 3 is 5, then this small distance must be what? X minus 5. Okay. But then let's check. So that one is also going to be counterclockwise. So plus 28 into x minus 5. Alright? Okay. We have not added the moment. So the moment is also plus m of x to the 0. Now, interestingly, means that 18x minus 14x minus 2 minus 28x minus 5 is what? No, that is it. Alright? Okay. So then m of x is going to what? 18x 14x plus 28 minus 28x plus 28 times 5. What is that? That's 140, right? Alright. So 18x minus 14x minus 28 is minus 24x. And then 28 28 plus 140. So 168. So minus 24x plus 168. Alright? Okay, so that is the moment function for the section which I have taken. All right. So now it is time to draw the shear force and the bending moment. Okay. So I have to copy the diagram, but this time around it's going to be easy for us because we have done all the necessary good work that we need to do. All right. Okay, so okay. So now we have to draw the shear force and the bending moment diagram. So all what I'll do is that I will just extend this here. Okay. Then I'll say that this is, let's say, my zero line for the shear force. Okay, this is my zero line. Okay. So first of all, let's begin with the shear force. So let's go back. So let's go back. Okay. So at point A, what was the shear force for the first part between A and B? So this is between A and B from 0 to 2. So the shear force was 18. It didn't depend on any so it didn't depend on the distance. So everywhere from A to B it was 18. So we have to say that from A to B everywhere it was what? 18. That's all. So 18 kilonewtons. Which is telling us that the shear force was constant from A to B. Right? And then we are going to ask ourselves from B to C, what is it? The second diagram. From B to C, it was 4. Okay? So it's like you are at 18, now you drop to 4. Is that right? So you are at 18, and then now you drop to 4. So it's going to look like this. So you are at 18, and then now you drop. So it's going to come down, and this is 18, right? All right. So now you have dropped to 4. So this is 4 kilonewton. And then in the last part, you drop down. So in the last part, what is this the shear force? That is this one. In the last part, you drop to minus 24. Meaning that in the last part, it came down all the way from 4 and dropped to minus 24. Alright? So in fact, this is the graph which shows the directions. Okay, of the shear force. All right. So we are done with the shear force. But this is minus 24. Now we need the bending moment. We need the bending moment. Again, let's call a zero line here. All right. Okay. So what is the moment? So for the first one, the moment was what? 18x. So come back here. And then this is what? So don't forget that the distance from here to here is 2. And then the distance from here to here is 3. Again, this is 2, right? All right. So okay. So what this means is that if the bending moment as a function of x for the first one, what was it? It was 18x. It means that at x equals 0, the moment was 0. So the moment was increasing linearly, right? 18x. It means that the maximum we can get will be at x equals 2. And that is what? In fact, that is the same as the area under this graph, which is what? 36. 18 times 2. Alright? Okay. So this is equivalent to drawing a line. Because if I have 18x, then it is like saying that I have got a line with a slope of what? 18. And then x is going to change from 0 to 2. Alright. Then I am done with from 0 to 2. And then I'm going to move all the way from 2 to 5. So from 2 to 5, this is what I want to do. I will go to the next one. Okay, I'm done. So I will go to the next one. Okay, 2 to 5. Yes, this is it. So from 2 to 5, this is the moment. 4x plus 28. But x is varying from what? 2 to 5. So 4x plus 28 means that if I want x equals 2, I'll put it there. So put 2 into 4x plus 28. So it's going to what? 4 times 2 plus 28. And what is 4 times 2 plus 28? So 4 times 2 plus 28 is 36. Alright? Is that right? Okay. So I have okay, wait. This one was what? 36, right? Now I have 36 and then let's not forget that interestingly, if you put if you put 2 here, you are going to get 36, which is the minimum moment between so the second, this is what I'm trying to say. If you put 2 here, you're going to get 36. And from what we already have, what do you see? So you see that this is actually what 36, which is already there. And then the maximum. So the maximum moment is going to occur at x equals what? At x equals 5. So I'll put 5 into this equation. So at 5, it's going to be 4 times 2 plus what? 28. Sorry, 4 times 5. And what is that? So 4 times 5 plus 28. And what is that? That is 48. 48, right? So it means that the maximum moment will be 48. Alright? So this is 48 right here. And everything is in kilonewton meter, please. And this one is in kilonewton. Alright. So we are done with that part. Okay. Now finally, let's look at the last part. Okay. This one. So what do you think will be the minimum? So the minimum was x equals 5. Don't forget that the section is between 5 and 7. If I put 5 into this equation, it's going to be minus 24 times 5 plus 168. And this will shock you. Watch this. Minus 24 times 5 plus 168. Right? You are going to get 48. If you do it correct, you are going to get 48. And it will shock you that the 48 is exactly what it means. Which is telling us that at x equals 5, it is correct. Right? Because this is 0, this is 2, that is 5. So that is correct. Yeah? Finally, you want to put x equals 7. And let's see, you will see something and it will surprise you. Plus 168. Put 7 there. And then if you put 7 inside, what do you get? Yeah? 0. You get 0, right? Now, if you get 0, then it means that it will send you back. So it means that at this point, the moment will send you back to 0. Okay. So it will send you back to 0. So in fact, this is the shear force. Bending moment. Okay. This is the bending moment. Okay. So that is it for you. Thank you very much for watching. Um, so we were able to cover several steps. In the next tutorial I will do on this series, I'll look at the more circle. We are also going to look at the second moment of area. But then before I continue with the next lecture or in the next tutorial, I will solve another question on shape force and bending diagram, which is one of the difficult questions. Alright. Okay. So thank you very much everyone for joining. And have a wonderful and pleasant evening. Thank you all. I'm ending the stream now. Thank you. If you have a question, please feel free to reach out to me. Thank you.